A pleasant morning to all. I am Dr. A.S. Krishnan from the Faculty of Mechanical Engineering, Coimbatore Institute of Technology, Coimbatore. My co-author, Mr. Shyam Sundar, is a former student in Mechanical Engineering and is right now pursuing his master's program at TU Delft. I will be presenting on a holistic approach to design of systems and processes. This is the overview of the presentation. We'll have an introduction followed by the concept of holistic with a simple illustration. Then we'll have a brief literature review. Then we'll try to discuss more in detail on what is this holistic perspective. We'll look at then the layered approach. What is meant by a layered approach, how it works and all. The next topic we'll discuss is on networking. Then we'll conclude and also indicate the scope for future work. What is meant by holistic? Some of the dictionary meanings of holistic are all-inclusive, complete, general, rounded, full, etc. But why do we need a holistic approach? Many of the real-life problems need multiple views. When we look at a problem from multiple views, we are likely to get a better solution. We are likely to get a better picture of the problem. For example, a cylinder looks like a rectangle when viewed only from one side. When we view from the other side, it looks like a circle. A few other examples in life are choosing a car, choosing a career, and choosing an education institute, choosing a life partner, etc. Okay. And some of the parameters what are generally considered for this holistic view are economy, exergy, entropy, etc. Okay. Then how do we fix the boundaries for holistic? How holistic is holistic? There's actually a limit by what we can perceive, what can be perceived by us. And this is likely to evolve and it should actually evolve. To understand a little more on holistic approach, let's consider transporting 72 people from one location to another which are 500 kilometers apart. The resources at our disposal are an airplane, a bus, and a car. The airplane needs to make only one trip, while the bus and the car needs 3 and 35 trips respectively, including empty trips. Apart from the number of trips, the table also shows the fuel efficiency, fuel consumption for one way, the total fuel consumed, speed, and time for transporting 72 people. Now, how do we choose the mode of transport? Time, cost, and the number of people to be transported are some of the parameters that are generally considered. The third option can be ruled out as it is outperformed in a humongous way. So we are now left with two options, the airplane and the bus. Depending upon the time or cost, we can choose one. The airplane could still be the choice if we choose both time and cost as the fuel consumption of the bus is more than 1 by 25th of the airplane. But the airplane could lose out if maintenance too is considered. As a traveler, maintenance and environmental effects are seldom considered. They are however needed from the view of sustainability. We'll now have a brief review of literature. Rachel in a book, Silent Spring in 1962, documented the environmental deterioration caused by synthetic pesticides. Her work actually led to the nationwide ban on DDT as pesticides for agriculture in the United States. And Hatton, in 1968, laid the importance of non-technical aspects of population problem. He in fact begins his paper by the statement, the population problem has no technical solution. It requires fundamental extension in morality. Sustainability was formally defined as development that meets the needs of the present without compromising the ability of the future generations to meet their own needs. This was given in the Brundtland Commission report in 1987. In 1993, Nicholas in his work placed entropy amidst economics, and he used entropy for comparing completely unrelated processes. Then in 1996, the legendary thermal science expert Professor Adrian Bejan stressed upon the use of minimum entropy protection. So based on the above literature, in this study, change in entropy was chosen as a parameter of ranking the sustainability of a process or a system. Just to have a glance of a couple of notable environmentalists, Rachel Carson and Nammarwar, both are biologists. Rachel is from US and Nammarwar from Tamil Nadu, India. What is this entropy-based holistic view? Let's consider a process or a product A, say airplane itself. Entropy is generated during its regular operations and maintenance. It is also generated during manufacturing of the plane and in decommissioning too, whether or not we like it and or consider it. So the total entropy change is a sum of all the entropy changes in these three stages. Let us now consider product B, say a modified version of the airplane that was considered earlier. B can be turned better than A if it has a lesser change in entropy. What we saw in the last slide was the basic concept of the entropy-based holistic approach. Let's now dig a little deeper. In the example of an air trap, the regular operations form the layer 1, the innermost layer, the primary operational part of a process or product. For example, in the transport problem, there's a entropy generation that is associated with combustion, air conditioning, drag, etc. How do we find out the individual entropy changes and then add them together? Okay. Coming to the layer 2, production and maintenance of the aircraft, they form the layer 2. We know that any lapse in the production and maintenance could result in a catastrophe during a regular operation. In terms of entropy, any reduction in the generation of entropy in layer 2, that is in production and maintenance, has a potential to significantly generate entropy in the layer 1, that is in during a regular operation. Then decommissioning or disposal of the aircraft comes as layer 3. It may not affect layer 1, but it does interact with layer 2. To understand what could be layer 4, let us take a simpler example. Suppose that we have a choice for water bottle. One is 1 liter, another one is a 5 liter water bottle. For this, the layer 1 is the primary operational part of a process or product. It's quite obvious. It is we have two subdivisions in it. One is filling and refilling. Other one is lifting it up to drink. Protection and maintenance, and of course disposal too, could form the second layer. And there is a possibility that the 1 liter water bottle could have a higher entropy generation because the number of caps required are more. Let's come to layer 3. Layer 3 has spatial and temporal consequences of direct association with the process or product. For example, the space that is being displaced. Then another one is accidental hitting of the filled water bottle against a brittle object. The spatial and temporal consequences associated with layer 3 of the layer 4. For example, the entropy generation because of breaking of the brittle object. It should be kept in mind that actions in layer 3 are always not accidental. They could be missed and sometimes deliberately too. What needs to be understood is that layers 3 and 4 are quite subtle and tend to have an influence in the longer run, and possibly they could be quite significant. We have just discussed a simple example of a water bottle. Life always is not so simple, but we have made it complex enough. If we take two components or processes that are associated with each other, their influence over each other can be portrayed as shown in this figure. So the third layer of P could influence until the second layer. Of course, it casts a larger influence on the third layer. Okay. and vice versa can also happen. In general, a process or product A is associated with multiple B's, and so are B's in turn. They may have C's associated with. So this necessitates the construction of what is called as an entropy network to have a holistic view. To conclude, obviously ranking a process or an equipment to be energy efficient at the system level may be attractive for us, but it paints a beautiful portrait that is far from the actual. Number two, the method of holistic networking and a layered approach to determine the entropy increase spatially and temporally for design of systems and processes could provide a sustainable solution. Then, number three, optimization of a process must not only involve ma- making the process more efficient but also aim at reducing the global increase in entropy in all of the concerning association and the consequences. So, as future work, we can try simulations on entropy networking that is as wide as possible in terms of time and space. And the requisites are huge computational resources and, more importantly, interdisciplinary and highly integrated approach at a global level. Now, these are some of the references. I would like to dedicate this presentation to my late friend Dr. K. Srinivasan, who was a scientist at CBRD, who was a very open-minded and a very simple person, who was also a mentor with whom I have discussed many of my research interests, including the concept of holistic approach to systems and process. Thank you so much for your patient hearing, and we look forward for your valuable views.